Let's use the same example to illustrate how Poisson reverse works. So taking one step back, before we have the link cost change. Now z here will discover a shortest path to x this way, z, y, x. So shortest distance from z to x is 5, and the next hop router is y. Now, link xy here, the cost changes from 4 to 16. X, Y, these two routers being connected to the link will be able to discover the link cost change. But Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, when we're calculating the shortest distance from Y to X, we ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to X, therefore we do 1 plus 5, and we ended up having 6 here, okay? A funny value for the shortest distance from Y to X, which we see from the network after link cost change, there's no way this is the right value. So to avoid having confusion such as this, we should stop Z from keep telling Y this is the shortest distance. So Z tells Y instead, the distance to X is not 5, instead being infinite. And that is what you're seeing here. Distance from Z to X at Y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. If this node here discover there's a route coming from the neighbor and using itself as the next hop. So if Y here discover in one of the neighbor, and this neighbor is using itself as the next hop to a destination. Set this entry here in Y's table to infinite. With now the Zx being changed to infinite, the way we calculate dy in iteration t0 will be different. So dyx particularly is the entry with different value. It was previously 6, but now let's see how it's going to look like. From Y to X, there are two possible neighbors, X and Z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor X to destination X, dxx. From second neighbor Z to the destination X, dzx. dxx, dzx. Let's look up the table. Xx 0, Zx infinite. So 0 here, infinite here. Comparing the two, 60 better. Therefore, shortest distance from Y to X is now, the direct link XY. And then the next point in time in T1, Z here is going to receive the distance vector from X and Y, and this time dyx is 60. That's going to change the result of the dzx, this entry here. So let's see, dzx. From Z to X through two neighbors, link cost being 50 and 1. 50 and 1. The xx and the yx, the xx, the yx. So xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wings. And you see here from Z to X, yeah, we're taking just this link, ZX, as a direct path to destination X. Quite different, isn't it? So we update DZ, and DZ is going to go to the neighboring nodes. Okay, and so Y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx. Okay, two neighboring nodes. 60 and 1 are the link cost. The XX, 0. The ZX, ZX, entry value being 50. So 51 compared to 60, 51 wins. So to go from Y to X, now the shortest distance is, this path. And in fact, at this point in time, so let's update the distance vector for Y. At this point in time, the network converge to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.